Thank you so much. Thank you for the invitation. I'm having a lot of fun. I'm going to talk about something different. So it's game theory. I'm not assuming that you know anything about game theory, so I'm going to start with a problem that you might all relate to, which is board games for date night. So we're supposed to choose a board game and are supposed to choose a dessert that is fitting for the board game. So that example is taken from a wonderful review by Ursula, Elliptic Curves Come to Date Night. And yeah, I like this example because it's kind of a relabeling of a classical example in game theory called Battle of the Sexes. And it's not a nice name, I think. And then now we're going to call this board games for date night. So this is a 2x2 game. That means we have 2 players, and each player has 2 strategies. In this case, we have a pair, Villa and Kara. And Villa is supposed to choose the board game for date night. It's either Wingspan or Carcassonne. So 2 strategies over here. And Kara is supposed to bring dessert at home. So it's either waffles or cookies. Then this is encoded in this matrix form. This is a bimatrix form. The way to read it is the first entry is the payoff for player 1, which is Villa in this case. And the second entry is the payoff for player 2. It's Kara in this case. So you can already see that some combinations are preferable in this case. So WW, Wingspan and waffles, are apparently fitting. And Carcassonne and cookies are also fitting. And in other cases, they're fine, but it could have been better, right? So that's an example of a normal form game in game theory. And when you have a situation, a social interaction like that, you might have strategies, right? You can say, I'm going to deterministically act on, putting on the Carcassonne on the table, or I'm going to, maybe with some mixed strategies or for probabilities, going to act on some strategy. And I'm going to denote those things as points in the product of standard simplices. And here we have one-dimensional standard simplex for Villa and one-dimensional standard simplex for Kara. And in this talk, I'm going to call them probability simplices, right? Because these are probabilities here, or it's called mixed strategies in game theory. And these are going to be also my variables, and then I'm going to work with them algebraically. And the labeling is as follows. The upper indices are always about which player that I am considering, and the lower indices are the strategies. So for example, P11 here is the probability Villa, player 1, chooses Wingspan. So that is basically the meaning of the variables. So you can already see that some strategies are better than the others. For example, W and W, cookies and or CC, are good strategies, and they're the whole Nash equilibria of this game, which we were going to define formally. But you can already see that in this matrix form. The idea is that, let's say that I am Villa, and I do not know what Kara will do. I'm just going to assume, for example, that she's going to bring waffles home. And I'm going to think my best strategy given that situation. So what is my best strategy if Kara brings waffles home is to put Wingspan on the table, right? So this is going to be my best strategy. And I can do the same thing for the case that I'm assuming Kara is bringing cookies home. So what is my best strategy here to put Carcassonne because 3 is bigger than 0? And Kara is doing the same thing at the same time. So all the players are looking at all possible strategies and maximizing their happiness in some sense. So that is the intuitive idea of looking at good strategies, which are going to be called equilibrium points of the game. Okay, so instead of these deterministic strategies, I can say, maybe I can take a point in the interior of the product of these simplices and then say, Villa is going to choose 75% of the time W, the strategy 1, and Kara decides 70% of the time to bring cookies home. This is strategy 2. So this could be also as, apparently a good strategy in the end. Or you can somehow use some kind of a coordination device, which is going to be just a coin in this case. I'm going to flip a coin and choose WW for heads and CC for tails because, maybe that's a happiness in the short term, but we want to be fair. Maybe 50% of the time you want to choose WW and 50% of the time you want to choose CC. Okay, so all of this intuitive idea is actually could be understood algebraically. So what we are doing is that we are writing down an multilinear equation here for each players. So it's pi w and pi c. These were the variables coming from the probability simplices. And these are the entries of the payoff matrix that I gave in the beginning. So these entries here. So I have 2 times 2 matrices for each player. And what I'm doing here is just vectorizing my matrix and taking the dot product with this vector of the probabilities or strategies and getting the expected payoff for each player. And in the end, we want to maximize these multilinear equations. And here is the picture of these points that we found under this map. So under this, this is a linear projection here. And the yellow part is the probability simplex. So I'm just a product of probability simplices. I'm taking the projection, linear projection under these 2 maps. And these 3, 6, and 7, 3, they correspond to CC and W. And I have the flip coin in the middle of this edge. This is the fair choice, which looks like a good one. And I have this red one, which is also actually an equilibrium point that we're going to see, but it's much worse than the others. So usually game theorists are more interested in these so-called Pareto optimal ones that you want to maximize your outcomes as much as possible. Okay, so that's basically the idea, so which kind of problems that, for games in normal form that we are considering. Well, I want to do it maybe more official. For general games. So what is the setup for general games? We can do that for any finite games. Here I'm choosing n players and then calling a game d1 times ... the n game. So that means player I has the I pure strategies. We had the smallest example. This was a 2 times 2 game, Ville and Kara game. We have, again, variables coming from the product of simplices. So each player gets a probability simplex that is encoding the mixed strategies. And here is my notation again, pk to the I. So that's the probability. Player I chooses the pure strategy k from the given strategy set, from 1 to the I. And a normal form game is given by n payoff tensors in this case, because we have more than 2 players. And this is, I'm going to denote it as x to the I here. And in our case, we had W and C. They were 2 times 2 matrices. And then in general, we have the expected payoff for each player. That is this big sum. This is the multilinear equation again. Okay, so that's the general setup. And the definition of Nash equilibrium that we already saw a little bit, the intuition, is as follows. So you're taking a point in the product of probability simplices that are corresponding to the players' mixed strategies. And that is called a Nash equilibrium for an n-player game if none of the players can increase their expected payoff, which is this map here, by changing their strategies to another one, while assuming the other players have fixed mixed strategies. So I do not know what the other players are doing. As I showed in the example, I'm assuming there will be cookies for dessert, and then I'm just looking at my expected payoff and seeing if there's any other thing that I can do, any other point in the probability simplex that I can take that will increase my expected payoff. And if it's not the case, and if it's not the case for all players, that's going to be an equilibrium point. Okay, maybe any questions up to this point? Are you all familiar with game theory, or is there anyone who's familiar with game theory? A little bit, okay. Okay. So So this is all you need to know about game theory to understand the rest of the talk, I hope. So let's see. Good. Why is this interesting? So this started in 1928, a little bit history. So existence of equilibrium was first proven. That wasn't called Nash equilibrium back then. It was just called equilibrium. It was proven for any zero-sum games by von Neumann. And in the 50s, Nash proved this for any game, any finite game. And after that, people started calling it Nash equilibrium. It's in the 50s, and then he got the Nobel Prize for this paper. It's a 2-page long, and then he uses this fixed point theorem from topology to show the existence. For any finite game, there exists one Nash equilibrium. So this is very inspiring because like a classical result from topology is coming to a complete other area of mathematics game theory, and it gives you like the solution of a big problem. So this is what we are also motivated with. We are also trying to do that somehow with algebra and geometry. So this started already in the 90s. So we can study Nash equilibria via systems of multilinear equations. So these are the multilinear equations that you need to solve to find Nash equilibria. After solving these d1 plus dot 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 dn multilinear equations, you still need to check some non-negativity conditions. So you still need to check these parenthesized expressions to be non-negative, and this was a probability, so this needs to be already non-negative. So it's not purely algebraic, but it comes with a bit of a combinatorial case-by-case checking complexity. Okay, let's go back to the example. Maybe this is kind of a little homework type of a thing that if you're interested in like how to get Nash equilibria by solving equations, this is one of the smallest games possible. So here are these big equations that I showed you. It's nice multilinear equations that I need to solve. And for the solutions, you still need to check if they're satisfying these parenthesized expressions to be non-negative. And if that is true, that's going to be a Nash equilibrium of your game. Okay, so this looks, I don't know if for you if it's looking easy or not, but it's actually looking kind of innocent, but it's not very easy to do in general. And this was already classified as PPAD hard by Papadimitriou in 1994. So what this means basically is it's quite close to NP complete, but it's not NP complete because we know there exists one Nash equilibrium. We know the existence of it. This just says that it could be very hard to compute. But, so finding one Nash equilibrium is fine, but finding a second one is actually NP complete problem. It's pretty, computational is a heavy problem in general. But what we can do is, of course, we can use symbolic computation, numerical computation. We can use Macaulay too. We can use Julia, and in particular, homotopy continuation package to find these points. And if you want to look at it, there's an example that I wrote a couple of years ago for a 3-3-3 game that is pretty fast, like a couple of seconds that you find Nash equilibrium of a game. Okay. So we already found a nice connection of Nash equilibria to real algebraic varieties. One thing maybe I didn't say is that these, maybe I wrote here, is that these are already always real matrices or real tensors. Because it makes sense, right? In applications, you have the payoffs to be real numbers. Okay, so that's why we have these nice connection of finding Nash equilibria to real algebraic varieties. Okay, so Okay, here I told you that I have to check some non-negativity condition. Let's say that if I don't have to do that, let's say that I'm looking at the solutions that are in the interior of my probability simplex. So I can get rid of this, combinatorial complexity, basically, and then just give an algebraic model for finding Nash equilibria. And this is what happens here. We just check these parenthesized expressions to vanish. And I had these pi i's in these expressions, and I just eliminate them. In the end, I get these nice, again, multilinear equations in d1 plus dn variables, and this many multilinear equations. So I need to solve these now without checking anything, non-negativity or so, to find Nash equilibria. So I want to get a square system that I can, use some techniques from algebraic geometry to do that. And I can eliminate more this last variable, because this is basically a probability. It can be written as 1 minus the sum of all others. And I get a square system of d1 plus dn minus n multilinear equations in the same number of variables. It's going to be a nice system that I can use BKK theorem, if you're familiar with that. So what you're doing is you're taking your equation, taking the Newton polytope of that equation, and computing the mixed volume, which is not always easy. And this is going to give you an upper bound for the number of solutions of this system. Okay, so this is a multilinear system. That means the Newton polytopes are actually nice. So they are product of simplices again. So we got rid of this combinatorial complexity, but we ended up again with a combinatorial problem. And here what we're doing is that, so Newton polytopes of these multilinear equations are in this form of simplices. Now I have to compute the mixed volume of these product of simplices to give an upper bound for the number of Nash equilibria. So it becomes also an interesting problem that was not solved before in game theory. I know it's a lot of new things, so please ask me any questions that you might have while I'm sipping some water here.
I just wanted to make sure I'm understanding. These are all, so the equations all have degree 1 on each variable?
Yes.
I'm not taking any powers on any of the variables.
Yes, sorry. So yeah, that's the notation that might be confusing. So when I have these x's, xi, and bunch of lower indices. So these are real numbers. And the upper index in my notation always indicating which player that I am considering. So this is the payoff of player I when player 1 chooses J1 strategy, ... player n chooses Jn strategy. And then when you have the other ones, let's say Pi, K, these are not powers, yes. And these are, again, this is a variable. This of player I. Player I, the probability. Player I chooses strategy K from this set of strategies that they have. So this is really a multilinear equation. This is square free. Okay. Good, so that was already done. So finding an upper bound for the number of such equilibrium, which we will call totally mixed ones. These are just the strictly positive probabilities, can be given as by computing this mixed volume, and this has a very nice combinatorial description. So what we are doing here is that we have these boxes, let's say, from 1 to n. So Bi is the ith box. And here I have my variables that we saw in this big multilinear equation, bk to the I. So for each player I have the I minus 1 variables because I eliminated 1. And what we are doing right now, this combinatorial counting, is that I want to put these variables in the ith box such that the number of variables in the ith box will be di minus 1. And I cannot put any variable into the box bi with the upper index I. So I'm counting how many of these block derangements that I can do for a given game, and that's going to give me a nice combinatorial formula for the upper bound for the number of Nash equilibria. Maybe in a picture it's nicer. So here I have my boxes. So it's the first box. This should have the 1 minus 1 many variables that I should put in. I can choose variables with an upper index p to the 2 or p to the n, but I can't choose the ones with the p to the 1. And I do this for all other boxes. So nth box will have the n minus 1 variables, but it cannot have any variable with an upper index n. If you have a game where each player has 2 strategies, that's going to be exactly the number of derangements of a set from 1 to n. This is like a nice combinatorial formula. Okay. Well, we can do that for 2-player games, like it's the first example. If I go back to the equations again, here, these are multilinear of degree n minus 1. So we're removing one variable in the middle, right? That is coming with the 0 and the Newton polytope. And if I have a 2-player game, this is going to be just linear equations. So I'm just going to solve a linear algebra problem to find Nash equilibria. And this is also, we can see that with mixed volumes. For a D1 times D2 game, we have these simplices, basically. And if the number of strategies are the same, then the mixed volume is 1, and otherwise it's 0. So it's solving a non-homogeneous linear system by row echelon form, and then we know that generically the system has either 0 or 1 solutions, right? So I'm saying generically. This we saw also yesterday in Colleen's talk, that sometimes intersections might be empty. Here I'm considering a nice intersection, so a nice square system. So you might have a square system where you don't have finitely many solutions. You might have other solutions as well. Like in the linear algebra case, we might have a solution as like an one-dimensional space, right? But what game theorists do is they just assume that the system is nice and the number of solutions are finite, or we have isolated Nash equilibrium. Okay. So it's interesting because here we have the mixed volume 0. So we do not have any totally mixed Nash equilibrium. So we do not have any in the interior of the product of simplices. But we must have somewhere else, because by Nash's theorem, we know that there must exist another Nash equilibrium. And this might lie on the boundary somewhere of the probability simplices. And this is a little advertisement, as Akiyoshi did yesterday, of a paper with Hiro and Luca. And we are looking at this problem with vector bundles. And this is basically giving us the opportunity to look at the non-generic games. So when you not have these finitely many solutions, which kind of solutions you might have, which kind of varieties that you might get out of it. And in particular, if you have an n-player game where you order your number of strategies from D1 to Dn, for a generic game, there exists no totally mixed Nash equilibrium if and only if Dn minus 1 is bigger than the sum of all other strategies minus n plus 1. So if one of the players have too many strategies, then like the sum of the other players, then it's somehow unbalanced that you don't get any strictly positive Nash equilibrium. And this is really actually an intersection theory problem in the end. This is a very nice description. Right. Okay. Before I go to another more combinatorial part of the talk, any questions? Okay, so this is more algebraic maybe, and here is another combinatorial object, which is called correlated equilibrium. So we already saw in the definition of Nash equilibria that we have some kind of a non-communication to the other players. We do not have any dependence to the other players. We do not know what the others are doing, but we are just simultaneously maximizing our expected payoffs. And this might cause some problems. If you heard about prisoner's dilemma, that is, the equilibrium points are not the best outcomes for players and so on. And that's why there has been many other notions were introduced, one of them being correlated equilibrium, which is not solving prisoner's dilemma, but solving other situations in game theory. And this was also a topologist, and he introduced this notion of correlated equilibrium in 1974. And this is somehow like an indirect dependency, some correlation between the players that we have. And for this, I have a little bit of a different notation here. So since I have a correlation, instead of considering the product of probability simplices, I'm considering one probability simplex. So there's some kind of a collective action. And this is basically the set of joint probabilities. It's Pj1 to the Jn, where player 1 chooses the pure strategy J1, player 2 chooses the pure strategy J2, and so on. And in the old notation, so this is now, for example, 2 times 2 game, P11 to P22, that is equal to this product. And some of you maybe recognize this. This is the Segre embedding, P1 cross P1, or take the kernel of it, that's going to be the ideal defining it. And this is no coincidence that we're going to see in a picture how this is relating to Nash equilibria. And the formal definition is as follows. So we take a point in this probability simplex that's going to be called a correlated equilibrium, again in the same spirit as Nash equilibrium, if no player can increase their expected payoff by breaking their part of the agreed joint distribution. This could be something like a third party coming to the game and giving some suggestions to the players. That's the correlation. And then we're still assuming that the other players are having mixed fixed strategies. So we had already an example of that. So we had this flip coin, and then this was kind of a recommendation that we're giving to us, and then we look at this recommendation, heads or tails, and then looking at our expected payoff, and if we cannot do better than that, we take that recommendation, and this is going to be an equilibrium point. A nice thing about it, it's not a real algebraic variety, but it's a polytope. So the set of correlated equilibria is actually a polytope inside the probability simplex. And here is the nice H representation of this polytope, which might look, again, scary, but there's a nice pattern that you can follow with the sub-indices. And here's the picture that I was talking about earlier. Here, again, I have a 3-dimensional probability simplex in yellow. I have the set of correlated equilibria for the game 2 times 2 game that I showed you. It is the green polytope with 5 vertices and 6 facets. It's a bipyramid over a triangle. And then I have the Segre embedding in red that is intersecting my polytope and in 3 vertices. And these 3 vertices are exactly the Nash equilibria of this game. If you want to do this computationally, of course, you have an integer problem, so you have the polytope, and then you're trying to intersect it with a variety. This is not going to work for computers, but theoretically, that's basically what's happening. In particular, any Nash equilibrium is a correlated equilibrium. But we have much more, right? We had finitely many, and now we have infinitely many equilibrium points. Okay, so that was our example. Just these are the H representation. This is the H representation of our polytope. This is unfortunately not a lattice polytope anymore. Not a lattice polytope, but it's a nice H representation that we have, very specific. It's living in the probability simplex. Again, in this case, these are, I just plugged the numbers in, and these 3 red points, black points are Nash equilibria. They are the vertices of the correlated equilibrium polytope. And this has a specific combinatorial type. It's a bipyramid. Okay, is this a coincidence that these Nash equilibria lying on the, as vertices or on the faces? It's actually not, but okay, there was another slide I forgot. So this is two very strong results in game theory, in the intersection with real algebraic geometry and polyhedral geometry. So you might think that these equations that I showed you in the beginning, multilinear equations, are very specific. And this H representation I showed you, they're also very specific, but there are very nice universality results around that. And first of them is due to Data from 2003. And she proves that you can take any real algebraic variety, and it's going to be isomorphic to the set of totally mixed Nash equilibria of a 3-player game, or to another game that is n-player game where you have binary choices for each players. This is a very strong connection to algebraic geometry. And the second one is about correlated equilibria. You can start with any polytope you want, P in Rn. Then there exists an n-player game such that the projection of the correlated equilibrium polytope of this game is going to be equal to that polytope that you started with. So the projection is, I'm going to show you a picture, I guess, is that this projection under the expected payoffs that I showed you in the beginning, which is this one. Oops, this one. So here, the yellow one was the projection of the probability simplices. We had these 3 Nash equilibria, and the green one is the projection of the correlated equilibrium polytope. The previous result is saying that you can start with any polytope that's going to be equal to such projections for a game. It's pretty strong, so it's like we should use some results from polyhedral geometry or from combinatorics to attack these. Yes? No, depending on your payoffs, yes. But in practice, when we do computations, yeah, we always take rational ones, yes. Okay. You mean the correlated equilibrium polytopes, right? Not the projections, because, yeah. Yeah, projections could be any, yes. Okay, so the picture I showed you here, so we had the Nash equilibrium points lying on as vertices of my polytope. And in general, it's true as well. So you take a non-trivial game, doesn't matter what it means. It just basically means that you shouldn't take your, for example, payoff matrices to be constant matrices, because then you get the whole probability simplex and so on. And then this proposition says that Nash equilibria lie on the face of the correlated equilibrium polytope of dimension at most d1 times dn minus 2. So this polytope lives in the 1 times dn minus 1 dimensional ambient space. And this is interesting for computer scientists as well, because then there are some tools that they can use to approximate Nash equilibria by using these polytopes. If you know somehow where the points are lying on the face, and you can try to approximate these points. And that's basically the reason that we wanted to look at them more combinatorially. So for 2 times 2 games, it was already done by hand, that the polytope is either a point or this bipyramid that I showed you. So these are the 2 combinatorial types that you can get out of a 2 times 2 game. And then we wanted to look a little bit further. We did some computations with Ben and Marie, and 3 years ago already, by a lot of computations, actually. But if you remember, I talked about the genericity for Nash equilibria, because you want to have nice set of solutions, finitely many, and so on. And here also we needed some kind of a genericity condition. So we can't just look at the space of all games, and we wanted to look at it under some genericity conditions. And we did that with the oriented matrix stratification coming from the polytope itself. So we basically looked at the correlated equilibrium cone, and then look at the coefficient matrix, because this is nice, right? We have this AX is smaller than 0 as my polytope, and then we look at the cone of this polytope, and then look at the maximal minors. It's going to give me a sign pattern, and then this sign patterns will give me a region in my oriented matrix strata. And for each region, basically we did, we went and we took a point and computed the combinatorial type of this polytope corresponding to this point. And then, yeah, this was a heavy computation with SageMath, Mathematica, and Macquarie 2 all together. And for 2 times 3 games, we got this result in the end. And that is that if you had a point as a correlated equilibrium polytope, or you have a polytope that is of maximal dimension 5, so this is living in a 5-dimensional ambient space, and this maximal type has a unique combinatorial type, or if it's not full dimensional, your polytope is not full dimensional, then there exists a smaller game such that the correlated equilibrium polytope of the smaller game is actually combinatorially equivalent to the polytope that you started with. And then we kept doing a little bit more computation here. Is that it is with Mathematica. Again, a lot of random sampling is happening here. So okay, we know the first 2 rows. This was already known, and this is basically the theorem that I showed you. And then we did that for 2 times 4 and 2 times 5. I think it just stopped there. But already at 2 times 4, we saw that of dimension 7, we do not have the unique combinatorial type anymore. And then again, it just grows and grows. But the thing is that these combinatorial types that we are finding here are repeating themselves. So these 3 combinatorial types here in the last row is the same combinatorial type that we found in the 3rd row. So kind of a containment happening. So it just made us think if there's some kind of a reduction that we can do for if the polytope is not maximal dimensional, can we somehow reduce this to a smaller game? And yeah, if you want to check out, here is the code for all of these, like the mixture of SageMath, Macquarie 2, and Mathematica on our math repo of the Max-Planck Institute. Okay. So we actually conjectured this, and I was talking about that maybe a year ago in a conference, and 1 week later, Jan Drijsma just wrote me an email that he proved our conjecture. So maybe it wasn't a very difficult conjecture after all, or maybe he's genius. So basically, you can start with any 2 times n game and look at the correlated equilibrium polytope. And if this polytope is not of maximal dimensional, then you can find a smaller game, 2 times k game, where k is smaller than n, such that this correlated equilibrium polytope of the smaller game is maximal dimensional, and this 2 correlated equilibrium polytopes are combinatorially equivalent. So it basically says that, okay, you start with a game, you can just classify the polytopes that are of maximal dimension, then you can classify all polytopes. Okay, so this is done for 2 times n games, but we want to generalize that for any 2-player games, again with Jan and Linda. And there is another project going on that will be, I think, a week or 2 at IMSI Chicago. Danai is here, one of the person in this is for people, that they're going to look at the CE, so correlated equilibrium polytope for zero-sum games. So zero-sum game, I think I didn't tell you that this like rock, paper, scissors is an example of a zero-sum game. So one is winning, the other one is losing, so summing up to 0. So 2-player games, this is basically the this kind of covered, hopefully. And then we went 1 step higher and looked at the 3-player games and did a lot of random sampling again. for 2 times 2 times 2 games, so 100,000 random pair of matrices. And only of maximal dimension, we found this many, so almost 15,000 distinct combinatorial types. So trying to classify all of them is kind of, I guess, not possible, at least with this sampling that we try to do. And also the F vectors of these maximal dimensional polytopes are kind of, there. I don't see any pattern that looks kind of difficult to look at. So that's why maybe you have any idea about, dealing with rational polytopes or, the polyhedral geometry of this nice polytopes with a very specific H representation, please tell me that we can, do more on this. So this is wide open because this paper that I just mentioned over here that we put 2 years ago on arXiv was the first paper in this area that was written from our community. So there's a lot of papers in game theory, computer science, and many related areas, but I think we were not there. So I hope that we will be more working on this type of connections, and I will be really happy to hear your ideas on this stuck problem, basically. So that's it. Thank you.